All right, year 12s, this is a short video just to take you through exercise 9D, which is looking at the graph of the derivative function. So I'm just going to share with you now my screen where I've just got a cubic graph up there. So if we look at it, this is a cubic graph, and what we want to do is sketch a graph of the derivative function. Now we have to remember that the derivative function tells us what the gradient is at any time. So let's just have a look at the gradient itself, okay? If I go down to this left part of the graph here, right down on the left, if I sketch a bit of a line here to approximate the gradient, you can see that the line I've sketched there is very steeply positive, which means that the gradient function is going to be somewhere up here. I don't know where exactly, but somewhere up there. Now, if I move a little to the right, let's say to where the graph crosses the x-axis, and if I sketch the gradient just there, it's still steep and positive, but it's slightly less steep. So if I go up to where x is 2, I'm just going to have a new point that's just a little bit further down. Now, these points are not exact values at all. These are very much approximate. Now let's move just a little bit further along to a new point here. This is where y is 1. I'm just going to go to that point there, and I can see that the gradient now is less steep, but it's still positive. So it's moving down. So I'm just going to have a value somewhere that's a little bit smaller. Okay. But I can see that right here on this turning point, I've got a horizontal gradient. So at that point there, my gradient function, the function that shows what my gradient is going to equal 0, which means I'll have a point sitting right on the x-axis. So this is the point where I cross the x-axis. Now, basically what I've shown is that the gradient starts off quite steep, and then as I move closer to the turning point, it gets less and less steep. Now remember that steep for gradient, when I transfer that into a number, the steeper the graph, the higher the number when it's a positive gradient. The less steep the graph, the lower the number. So what I'm really expecting to see, oh dear, let's try that again. What I'm really expecting to, I'm working with my mouse, it's very tricky. I'm expecting to see this graph just move down towards the x-axis like that, and then cross at this point here. Okay, now what happens in between this first turning point and this second turning point? If I look at the graph, I can see the gradient is negative all the way along. That means that for this whole region, I am expecting values down here below the x-axis because the gradient of the graph is negative. So the original graph has a negative gradient, then the graph of the gradient will be below the x-axis. So right here, just to the right of the turning point, it's negative, but not too steep. So I'm probably going to expect to have a point just somewhere a little bit below the x-axis. Whereas when I get further to the right, it's going to get a bit steeper, which means it's even more negative. So I'm still moving down here, right? However, as I move further to the right, it doesn't get a lot steeper. It's still curved, but there's not a big change here. So what I'm going to see is that this curve will sort of head down and then across. Now, eventually it's going to turn and start going up. And I know it's going to keep going up until I have another turning point, because a turning point on an original graph tells me that on the derivative graph, I'm going to cross the x-axis. And that's going to happen just here. So if I join up what I've done so far, now it's looking like it's going to be a parabola, a very wonky parabola. But you can see that if I have a cubic, you know that if I take the derivative, let's say of x cubed, the derivative will be 2x squared. So when I take the derivative of a cubic, I'm always going to get a parabola as a result. So that will guide me as well when I'm trying to think of the shape. What I don't know is, where is this turning point? I know where it is in terms of x. It's going to happen as I head down this graph, when the graph stops being concave down and starts being concave up. Because when a graph is concave down, that means the gradient is decreasing. As I'm heading to the right here, the graph is still concave down, and somewhere maybe about here, the graph stops being concave down and starts being concave up, which means my gradient is now increasing. What I don't know though is the value of the gradient there. I can look at it. I'm actually going to estimate that it looks like more than -1, maybe something like, I don't know, -1.5 or even more. So probably if I take this, it's going to look more like that. But I really don't know. And you're not expected to know if you're not given more specific information about the graph that you're starting with. Okay, so I might just erase this section here. And we'll go with the new version. All right, now to the right of the graph, to the right of that turning point, my gradient is going to be always positive, which means that the graph of the gradient function, the graph of the derivative, is going to be always above the x-axis. All right, now what I can do, actually no, I won't, I'll go to the next one. Okay. Let's switch graphs. I'm going to rub out all of that and start with a new graph. So the main thing to remember is when I'm looking at my original graph, then I'm going to decide, I'm going to decide the shape of the gradient function based on the gradient of the original graph. So if I now look at the graph that I've got here, it's a straight line graph. So I start up the top here and I go all the way down, all the way down, all the way down. It's a straight line, which means my gradient doesn't change. And in fact, here I've got the numbers. I can see that my y-intercept is 0, 2, my x-intercept is 1, 0. So I can actually calculate my gradient, okay? My gradient is going to be, well, my rise is -2 and my run is 1. So my gradient is going to be -2, which means that what I can actually do is I can draw a much more accurate graph for my gradient graph. It's going to look like this. It's going to be a horizontal line going through y equals -2, because it doesn't matter what value of x I have for this graph, the gradient at any value of x along the graph is going to be -2, which means my derivative function is going to be y equals -2, which is a horizontal line going through the point y equals 0, x equals 0 and y equals -2. Okay, one more example. Now, this function has a negative gradient to the left of the y-axis and has a positive gradient to the right of the y-axis. But what it doesn't have is a 0 gradient on the y-axis. I don't have a horizontal gradient there. In fact, on the point x equals 0, immediately to the left of this, I have a negative gradient. Immediately to the right of it, I have a positive gradient. But on that point, it's impossible to decide what the gradient is. It's not something in between -1 and 1, because this, I can see this is going down, the gradient's -1 here and +1 here. It's not somewhere in between. It's not 0, because if I were to draw a gradient of 0 right on that point, that's actually not the gradient of the line. It never actually goes sideways. It comes down and then it goes up, but it doesn't have that gradual turn that you see in a proper turning point. So in actual fact, what we have here is an undefined gradient right here. I don't know what the gradient is. If I look just slightly to the left, it looks like -1. If I look just slightly to the right, it looks like +1. So this is what my graph is going to look like when I draw the gradient. It's going to be y equals -1 up to here. It's going to be y equals +1 up to here. And then, let's see if I can do this. We need to have a little, oh, I've missed it slightly, but you get the idea. We need a little open circle on those 2 points to show that when x equals 0, my gradient function is actually not defined. Okay, and that's the graph of the derivative function.